Alright, this is the presentation for our ECEE 352 project, which is an audio amplifier. I'm Connor Thompson.
I'm Zachary Jacobs.
And I'm Gabriel Breiva.
The goal of this project was to create an audio amplifier capable of creating 200 to 300 volt per volt gain and a frequency response in the audible range, which is about 20 Hz to 20 kilohertz. It was split into two parts, a preamp and a power amp.
The function of the first stage of our amplifier is to produce a gain of 20 to 30 volts per volt, and this part of the amplifier also sets the frequency range to the audible range of hearing. It will utilize a BJT transistor and a JFET transistor.
The power amplifier just sets a lower gain with a range of 8 to 10 volts per volt, and also boosts the current to be able to power the speaker overall. This circuit uses a Darlington transistors, BJTs, and VB multiplier.
This is the schematic for our preamplifier. The output is on the right after the C4 capacitor. The values that we calculated here will be covered in a minute.
For our preamplifier circuit design, for the BJT, the circuit is powered by 30 volts and it has an output of 15 volts. We decided to choose an IC of 3 milliamps for a neutral frequency response. And with that value, we calculated an RE of 3.3 kilo ohms to satisfy the voltage of the emitter to be 10 volts.
Good. From there, we calculated the RB1 and RB2, which are the resistors on either side of the base of the BJT. In order to calculate these, we used the fact that VBE was going to be 0.7, and VE is 10 volts to calculate that VB is 10.7 volts. From there, we realized that that IB, being very small, could basically be disregarded, and the current through RB1 would be essentially the same as RB2. Using that knowledge, we found the ratio of RB1 and RB2 necessary, which resulted in RB1 of 110K and RB2 of 62K.
For the JFET design, a JFET was utilized because it has an infinite input resistance. This allows for the input current to be low and to make sure that there's less distortion on the input signal. The feedback resistor was chosen to be 47 k ohms in order to choose our gain value, which we wanted to be between the 20 and 30 volt per volt range, and we chose 28 volts per volt.
This is the frequency response of our preamplifier simulated circuit. It has a corner frequency of about 20 Hz to 300 kilohertz.
Alright. This is our total power amplifier schematic. For this circuit, we utilized two Darlingtons and a VBE multiplier, along with bootstrapping capacitor and resistor in order to control the gain.
In order to calculate some of the values on the previous page, we calculated the values of the resistor in the VBA multiplier, which were the two BJTs in the center, in order to bias the Darlingtons to around a difference between the bases of about 2.8 volts. We later modified that value, but we'll cover that in the next section.
These are the results of the power amplifier in the simulation. This is in the time domain. So the red curve is the input to the power amp, and the bluish curve is the output. This shows about a gain of 2.93 volts per volt, which is a little bit lower than the objective.
This is our total power. This is our total schematic, integrating both the preamp and the power amp. The preamp output is used as the input for the power amp, and we used 30 volts to power both circuits.
Alright, these were the simulated results of our full schematic. The black line is the input into our preamp, the blue line was the output of our preamp, and the red line was the output of our power amp. The preamp continued to show similar gains to what we showed in our original schematic, as did the power amp, for a total gain of around 79 volts per volt. This is lower than I expected, but was necessary to compensate for noise issues that we were having in our actual circuit. We adjusted the schematic to match the actual circuit to keep track of the changes we were making.
So this is simulated results of the power at the output of our circuit. The different peaks correspond to when each Darlington is in active mode, and the values are when the dead space in between when it's switching from the one Darlington to the other. And you can see that it goes from a higher peak to a lower peak because there's two Darlingtons, and the one was always peaking higher than the other, so it's just going back and forth.
This was our overall gain results. It's clear that from these values that our simulated results were slightly more successful than our physical values. The preamp gain of 27 was perfect in our range in the simulation, but became a value of about 48 in the physical circuit once we integrated it with the power amp. And that resulted in a 79 volt per volt overall gain in the simulation circuit, but a 37 volt per volt gain in the actual circuit.
The reason that we had so little gain in our actual circuit was because the 8 ohm power resistors that you saw in the schematic turned out to be too small in our actual circuit. With the 8 ohms, we were getting a large amount of distortion on our output signal, and while we were maintaining around 80 to 100 volt per volt gain, it wasn't able to properly drive the speakers and causing too much current flow through the Darlingtons. So we had to increase those values, but the only resistors that we had available to us were 82 ohm power resistors, which killed the power amp gain to about 0.8 volts per volt.
Some other sources of error in our project was that we disregarded the effect that the load had on the circuit, and the resistors and capacitors we had access to had a low tolerance, so they could be very different values from what we needed. And the biggest problem with the circuit is that the Darlingtons needed to have a large current through them, but they overheated and stopped functioning properly when that happened, which is why we had to add in the power resistors, which then lowered the gain.
Alright, and next we'll show the demo of our functioning